Just a warning, I had a cold last week, so my throat is a little bit rough. And I gave a seminar yesterday, and at the end I was almost miming. It was very quiet. So I'll do my best to project today. But we'll see how it goes. Okay, so again, everything here is joint with David Zureick-Brown and Emery. And today we're just going to fix a number field. And there's really going to be two cases. K is Q and K is not Q. So we're going to take a number field. And we're considering abelian varieties over K. So in particular, I want a principally polarized. This is just going to make life easier, at least for me, to state theorems. Principally polarized abelian varieties of a fixed dimension. And everything's going to be either trivially true or false if it's 0. So let's suppose it's positive. So some fixed dimension G. And defined over K, of course. Defined over K. Okay. And you lose nothing if you just want to think about Jacobians. You have a nice, smooth projective curve. You have its Jacobian. That's an example. And everything I'm going to do today is interesting in the case of Jacobians. Okay. So we can fix an integer and then look at the torsion subgroup. So this is the M torsion subgroup of A. So you can choose some algebraic closure of K. And as a group, as an abstract group, it's boring. It's just 3 Z mod M Z module of rank 2G. Right, so that's just, if you think of the complex points, and well, maybe you should make sense of that. Then this as a, I'll be really lazy, as a group is just a torus. So you can sort of just geometrically read off what the structure of the torsion group is. It's a very simple group. What makes these torsion subgroups interesting is they come equipped with extra structure, and that is an action of the Galois group. So we'll have the absolute Galois group of K. So automorphism to K bar that fix K, and we get an action on the torsion points, and it preserves the group structure. Preserves. And we can encode that in terms of a representation. And since the group has a nice structure, we can choose a basis. So this is only going to be well-defined up to conjugation. And once we choose a basis, we get a nice representation into this group. So for every M, we have such a representation. And then what we can do is we can make M, this integer, become more and more divisible. And we get a single representation which encodes all of these. So I'll just remove the integer from the subscript, gal k, and sort of on this side, I'm sort of taking the inverse limit. So I have GL2G, the profinite completion of the integers. So this is a single Galois representation. And for me to tell you how the Galois group permutes the torsion points of the abelian variety, that's the same thing as me telling you what this representation is. Okay, so this representation tells you everything about the action. It is interesting for lots of reasons. In particular, it knows the abelian variety. So from faultings, if I lost the abelian variety and I only knew this, I could go back and recover my abelian variety up to isogeny. So all sort of the interesting arithmetic is somehow in here. You just have to pull it out. And today, we're going to do something naive. We are just going to study its image. So we're just going to try to say something about its image. And just to make it clear, typically when people study these kind of things, they're interested in a fixed m or maybe a prime which can vary. I sort of want to say things about the entire Galois action all at the same time. So this is going to be some large infinite group. Okay. Great. So a couple questions I might have, and let me put them over here. So some kind of naive questions. How big can it be? So how big can this group actually be? Okay, and what I really sort of mean is in terms of the field and the dimension. So if you're looking at genus 5, dimension 5 abelian varieties over the rational numbers, how big can the image be? Another kind of question you might ask is if you restrict A to special families, so what is this Galois action when, say, A is the Jacobian of a, and you can use whatever word you want here, it's in quotes, so it doesn't really matter, random, typical, and then you can pick a family of curves you like to study, so I'll say hyperelliptic curve. Again, maybe with fixed G and K. So the first thing is we'll think of how big this can be. And usually with this sort of thing, it's as big as it can be once you know the obvious constraints. But first you have to figure out what the obvious constraints are. So in this case, it's never going to be GL2, GL2G Z hat. It's going to be always much, well, except when G is 1, it could be. But when G is higher, it's actually going to be much smaller. So let me state that, and for people who already know what I'm about to write, try to figure out what the answer is. So I'll get to this in 5 minutes, but you can try to guess what the answer is going to be. Okay, so there's a constraint, and that comes from the Weil pairing. So we have a Weil pairing on our abelian variety, and we can also have our polarization, our principal polarization. And together they give a pairing for each integer from the m torsion to itself into the m fruits of unity. Right? And it's a nice pairing, so it's bilinear, alternating, non-degenerate. And in particular for us, it also has it's compatible with the Galois action. So if we have an element of our Galois group, and we look how it acts on 2 points, and then take the pairing, it's the same as pulling this Galois action out and acting on the root of unity. And since this is a root of unity, it's going to be the same as taking this root of unity to a specific power, where this is the usual cyclotomic character for the m roots of unity. Describes how it acts on the m fruits of unity. Okay, so this constrains the image. So our group, our representation, takes the Galois group into something smaller. That's exactly the things that satisfy that. So GSP, AM, EM, and maybe I won't say what it is, but it's exactly the automorphisms of AM such that they have this property. When you act, it's the same as just raising to a power. And actually, I should write that because I need it. So EM here, this is the B, the automorphisms. Such that and some number up here I'll call the multiplicator. Just needed to give it a name. Okay, so it lies in this thing, and this is actually independent of A, and I'll give it the abstract group name, GSP 2G Z mod M. Okay. So the image is smaller than just every automorphism. It also has to respect the pairing appropriately. And of course, you can package them all together in a single representation, and it lands in GSP 2GZ hat. Okay? And here we have the fact that the multiplicator composed of our representation is the cyclotomic guy. And we have the same thing here. Oh, no M. This is just the cyclotomic character, which is going to describe the Galois action in all the roots of unity. And maybe I should, since this is Galois Q, more precise, restriction to Galois K. Okay, so Abelian varieties, you can look at their torsion points, try to understand the Galois action. There's one obvious constraint coming from the Weil pairing. And the question is, are there any others? And here's the first theorem. Suppose K is not Q, or G is at least 3, and then there actually is an abelian variety which has the biggest image possible. Then there exists a principally polarized abelian variety, A over K, of dimension G. Yeah, I can make it the Jacobian of a trigonal curve. Dimension G. Oh, such that the image is what you expect. It's exactly the things in GSB Z hat for which this multiplicator lands in the constraint we have. Okay. So in this, for these kind of abelian varieties, every sort of allowable automorphism of the torsion point, all the torsion points that respect the Weil pairing in the right way, actually arise via Galois action. Okay. And so that's one of the theorems. Just a remark, it's false for K equals Q and G and 1 and 2. Okay, so it's not true. So that should at least convince you that something non-trivial is happening, so genus 2 or dimension 2 abelian varieties, there's an additional constraint somewhere. throat's hurting. So if you have questions now, this is a great time. It's hard to say what random means. I mean, because the moduli space is, its k points is quite complicated, right? So really what the theorem is going to say is that if you look at if you take a general enough family of abelian varieties whose base is rational, then you expect this. It's not clear if it's true. If you well, you have to quantify what a random abelian variety is. Yeah, I guess if you count them by Falting's height, I think that's true, but we just don't know about the subvarieties enough to count the points, I think. Yeah, so for elliptic curves, Duke and a student of his show it's big as possible over Q. Yeah. And this remark for G equals 1 is an observation of Serre, that you don't get the full thing. Okay, great. So if you look, that's my next part. So families. So I'm just going to keep going. That was the next thing. So that's really what this talk is about. So I'm going to do a slightly fancier A to be my family of abelian varieties over some base space. So really, to prove this theorem, it's hard just to say, hey, here's the abelian variety I found. It's much more manageable to consider a whole family of them and then show most have the property you want. Okay, so we're going to consider a family of abelian varieties and parameterize by something nice downstairs. And I tend to like an open subset, open non-empty subset of Pn, because it has lots of points, and I understand the arithmetic of U very well. I don't have to deal with complicated base spaces. And this is going to be a principally polarized abelian scheme over U of relative dimension G. And then when you have a point downstairs, let me give it a name, F, the fiber is an abelian variety. So this is a principally polarized, exactly what we had before, abelian variety, dimension G, defined over K. So this is exactly the thing before. So this is just what I mean by family. So let's do a really easy example. So very easy example would be we could consider U just to be, let's say, G plus 1 tuples subject to the constraint that the corresponding polynomial is separable. And that's a closed condition because that's just saying the discriminant is non-zero. Of course, I'm defining the family of hyperelliptic curves. So that's a nice space. I can embed this as an open subset into P 2G plus 1. Has lots of points for me to count. And I get a family of curves defined by the equation. Right, so for every point down here, I have a curve, and it varies nicely in this family. And then for this, I can actually try to understand for a random U, and random in the sense of density. So there's a height down here coming from embedding into projective space. And if I consider points down here of bigger and bigger height, I can consider the ratio of those whose curve and its Jacobian has a certain Galois image, and I can really try to make a density 1 result to sort of say what the image is. So anyway, this will come back in a bit, but really we get a family of Jacobians too. Okay, so I'll come back to this example. Okay, so before I come back, let's go back to the general family I have. And just like in the introduction, we have representations, one for each m. And now, instead of the Galois group, we have a fundamental group. Okay, and I'll write it once. It's well, these are the tau fundamental groups. Right, so you can look at the M torsion Abelian subscheme. That's going to give a nice cover of U, which will correspond to this kind of representation. And if again, you can always package them together into one big thing. Great. And for a point, you can specialize, and you get a, well, let's say specialization gives an inclusion into this. Okay, so the point is just a map from spec K into U. So functoriality gives you a map from the Galois group of K into here, and composing, sort of you recover the ones we were talking about earlier. Okay, so for any family, and here I like rational bases because then I have lots of points to work with, we sort of have a natural upper bound coming from the geometry of the family. And sort of to prove that theorem, the main work is just to find a family which this is as big as it can be, plus some more. But okay, so that's our that's how these are all related. And this is sort of a theme that's familiar in number theory. It's kind of familiar to how do I say this? It's sort of the setup of the Hilbert irreducibility theorem. So typically you have your pi 1 mapping into a finite group. Here I've broken that, I have an infinite group. But if you had a finite group, then when you specialize, you get an inclusion. And that inclusion is a quality for most U in the sense of density. Okay, so naively, you think that this is going to be quality for most U. This is sort of what the Hilbert irreducibility theorem suggests to you. It usually works, and there's cases that we saw before where it breaks. Sure. Yeah. 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 You could. Yeah. You definitely. Yeah. You can have one parameter family. You could fineness or try to make it effective, which is what. Yeah. These papers with Kowalski and Ellenberg and Hall. Yeah. Do things like that. Okay. So now let me state sort of the overarching theorem. But before, I need one big assumption, just to make my life easy. So I'm going to have a big monodromy assumption, call it. So I'm going to consider that my family is actually pretty general looking. So it's that this guy, it's geometric, so I'll look at the geometric fundamental group. This, which now sits inside the symplectic group, because geometric part, the cyclotomic piece disappeared. And the assumption is that this is going to have finite index. So this is going to be essentially as big as it can up to finite index. And the hyperelliptic case is an example where that holds. Okay, so with all these running examples, the theorem is the following. Okay, so here's the weirdest assumption you might see in a while. Suppose our number field K is not Q. So this is going to be a theorem that holds for all number fields but Q. For most UK, and I'll put it in quotes, but most in the sense of density when we think about height of points. For most, the image, when we specialize and get the fiber in our family, so an abelian variety over K, this is as big as it possibly could be. So we had this constraint, and it's actually going to be equal. And the earliest one is just you have to find a family with monodromy as big as you can. And this is the more general setup. So for example, in our hyperelliptic case, you can show that this, oh, and now I realized that's not a random hyperelliptic curve because I have a rational Weierstrass point. Okay, so that's not a random hyperelliptic curve, but it's a nice family. And its image, monodromy, well, I'll just tell you information. It's big, so it contains all the elements it should. Oh, gal K. Oh, mult. So this is all conditions coming from the Weil pairing, for which B is the identity mod 2. So up to everything mod 2, it's as big as it possibly could be. But then the image of this group mod 2 is going to be isomorphic to the symmetric group on 2G plus 1 letters. So my family, I have a rational Weierstrass point at infinity. I have 2G plus 1 other ones. And the Galois action on those actually tells you the Galois action on 2 torsion. So this is actually smaller than you'd expect. So if you... Yeah, it's just images, yeah. Yeah, it's not, yeah, Zariski closure is easier. This is just the straight up infinite image, how does it act, the whole thing. Well, okay, so in words, you take y squared equals x to the 5 and then write a bunch of large integers as coefficients. High probability the image of the Jacobian, the representation coming from the Jacobian, will be this group. So that's kind of the idea. Okay. Sort of an arithmetic application. Let's not go too far. Let me stay close to this board. Just to say something which is not purely about the torsion points, suppose you have a curve like over here. So C over K, hyperelliptic curve. G is G. We have our Jacobian. And suppose we're in this, what I call a generic case, where is this guy. Then using this, one thing you can study is how does C sit inside the Jacobian. And what is its intersection with torsion point? So I guess I'm implicitly using the point at infinity as an embedding into Jacobian. And the Mann and Mumford conjecture, first proved by Raynaud. So Mann and Mumford says that this is finite, assuming we're high enough genus. So the curve is moving in the Jacobian, and it only hits finitely many torsion points, which are dense everywhere. And sort of in the case of this generic case, which I think I claim as sort of, if you can think of as a generic curve, the intersection is actually something you can write down. It's just the Weierstrass points of the curve. So sort of, you can use these theorems to sort of say what a random abelian variety in your family looks like, and then you can sort of have nice properties for random things. So that's just.
You make anything with your abelian varieties which aren't Jacobian, so you always use them.
I can do other way. Yeah, I can construct families of abelian varieties, which I can use, which aren't Jacobians. Yeah. That's something I'm trying to do for an application I'm not going to mention now, because it's on videotape. That's something I need to do, yeah. Okay. I'll give you a couple ideas of the proof, but first let me tell you what goes wrong with Q. Okay, so it's what's wrong with Q. And it's actually fun because most people study the case Q, so they get a kind of confused idea of what's happening. So in the case Q, and let me just have an abelian, go back to my old notation. It's not a family anymore, it's just one abelian variety. And let me give its image a name, just to simplify everything. Okay. Well then, I can look at the image of the absolute Galois group with the base field is the cyclotomic numbers. And again, this representation composed with this homomorphism I call the multiplicator is the cyclotomic character. So in this case, it's actually just going to give you the full group except those that meet the symplectic group. Okay. And then in K is Q, something kind of spectacular happens. That's that the cyclotomic field is actually the maximal abelian subfield, maximal abelian extension. Okay, so here, this is very Q specific. So here, my Kronecker-Weber theorem. And in terms of this group, this is going to be the commutator subgroup. So take all the commutators, take the subgroup, and take its profinite completion. So we get this forced equality of our image. And what happens for maximal case, if we just consider what happens if G was ever GSP2G Z hat, the possible image, largest thing possible, when G is 1 and 2, this fails. The commutator is actually much smaller. So that's what those obstructions were with Q. So the theorem of Q, which is the harder kind of to figure out, but it's what everyone was studying. Let me just copy. So now K is Q. For most points in my base space, which are classifying abelian varieties in my family, the image of the abelian variety of that fiber, well, I can't actually say what it is because it might be smaller than geometry expects it should be. So I can look at index in the thing I expected. And I can show that this is always equal to, oh, most of the time equal to a specific number. And it's just kind of relating these two groups I talked about. H. And the commutator. Yeah, so for elliptic curves over Q, this number is usually 2. So the image is usually 2 smaller than you expect when you consider just the general Weierstrass equation, y squared equals x cubed, ax plus ba be your family. Okay. Great. My throat's gone again, so if you want to ask questions, this is the best time. Yep.
So aren't we considering just the abelian variety over the generic point and then the representation of the Galois group of the function field of the base?
That's the same kind of, yeah, I mean, it's the same, just because if you have my map of the pi 1 of u and you specialize at the generic point, then you get what you said.
Okay.
So that's the different way of saying it. Yeah. Is that right? Yeah, it makes sense there.
Because it is.
Yep.
Can you weaken it?
I can, but we haven't. So I'm tentative to say, and actually I expect there are other obstructions lurking around, still coming from sort of Abelian ideas, but I think there are additional obstructions when you remove the big monodromy assumption. So I'm tentative to actually state anything publicly, but something else should be true for a general family, which is somehow geometric, non-isotrivial family. I guess it's true if it's isotrivial, just boring. Okay, so let me give you an idea of a couple ingredients of the proof. And there's sort of two pieces, small primes and big primes. So let's first think about small primes. And you really just kind of have to think about the L case first. So if you have big mod L image, you then have big L-adic image, it's just some group theory. And then it's a question of piecing it together, and they usually don't interfere with each other, but that's a different step. So the main thing is just to study these guys for L big enough. Okay, and so for small L, I actually mean something weird. I mean up to some strange bound, which will make sense when I talk about large primes. And I'm kind of interested in those u for which their height, and now I'm actually saying what I mean by most. The height of this point is at most b, and I have two variables. Let's call it x. And I'm studying those for which the specialization is smaller than I expect. I'm screwing it up. And I have some other constant here. I'm not telling you what it is. I really just want this image geometrically to be big too. So, which is it's not what I expect. So, and I'll just say FL to be quicker. Oh, for some L in my range. Okay, and then I'm really dividing all of this by the number of points of a given height. So that's quantity. And this is actually something you can compute, or not compute, but bound. And let me skip a middle step. Say it's big O over that. So it's going to use too much chalk, but the big thing is just to sum over all these primes and have the same condition. And then each of those I can bound using explicit versions of Hilbert irreducibility, because these are actually finite groups involved. So I'll just tell you. You can actually just write down bounds, and you have to say how they depend on things. So I'm choosing some auxiliary little number. Okay. So this is explicit Hilbert irreducibility. It's actually telling how it depends on L2, and it's sieve theory, so explicit Hilbert irreducibility. And you can see that this goes to 0 as x goes to infinity. Yeah, it's like that. Yeah, you can do a large sieve. So, okay, so that's the small primes. It's sieve theory, just making Hilbert irreducibility explicit. Then there's large primes, and that's what I want to finish talking about. Yeah, so there's sort of a Gorselema saying there's these, they don't match, so they separate. And then there's also the part coming from the primes I ignored, but they don't really interfere too much either. So yeah, it's kind of a Gorsat thing that pulls everything together, apart. Exactly. Okay, so the last thing I want to talk about are large primes, or what's happening most of the time. Really, I want to say this has density 0 where I allow all primes, but then the step where I break it up into a sum fails badly. It just explodes. So I somehow have to control the big ones. And I'm not going to work at the inequalities, but I'm going to tell you the main ingredient. So for the rest of the talk, we'll again just fix an abelian variety defined over K, dimension G, principally polarized if you want. And we're going to have one other assumption, just to make my life easy. We're going to assume that there are no extra endomorphisms, which that big monodromy assumption definitely means for most of my fibers in my families. Okay, so then there's a theory developed by Serre in the early 80s, and he gave several courses in the, I think, 84, maybe 83. He wrote some letters, but it was never published as a full thing. And roughly, it says we have these groups, which I've been studying. They're finite groups sitting in a matrix group. And these things look like, and here's where I'm vague, look like the FL points of a reductive group. So when you kind of do examples, you see patterns. You look at L big enough, and then you see, hey, this always looks like a certain group. They're not just kind of wild. They actually turn out to always resemble something else. Okay, so here's a actual statement of that that's not so vague. So we sort of had to go back and reprove it, making everything effective, because he always had one abelian variety, and we need to vary. And that means all your constants have to be good when your abelian variety varies. Okay, so the effective version There are constants. C, D, gamma. These only depend on the dimension, which is fine for us because when we consider our family, we're always have the same dimension in our families, our fibers, such that if L is big enough, and big enough is where some of these constants show up, so C is my constant. This is the degree of the number field. Here's what you mentioned here. This is the logarithmic Faltings height. So we sort of understand, it's the semi-stable version, so we understand how it varies in families too. In particular, we'll see on the side, if A kind of came from one of the things we've been studying, its Faltings height, you can bound it in terms of the height of the point. And then if you're considering points up to size x in terms of log x. And so here we're considering primes L, which are bigger than some constant times a power of log x, is why the small primes shows up. So this is, the previous case was the ones this theorem is going to exclude. Okay, so for L big enough, this group should look like a reductive group, the FL points of a reductive group. So that's what it says. So there is an explicit means you actually construct it. A reductive subgroup HL inside GL2GFL. Such that three conditions hold. One is just the bookkeeping. It breaks up nicely, so this is semi-simple. So, it's a yeah, it's connected. Reductive connected. Yeah. Here it breaks up into a semi-simple and a torus. In this case, the torus is just going to be the homophetes. That's coming from basically effective faultings in this endomorphism assumption. Two more. This is what look like means. Oh. One is, okay, so we have this group we're interested in. Well, I have lots of space in me. So now I have to argue why, well, explain what it means for this group to look like the FL points of H. Because they're just finite groups. That's the thing. So here we have that when we look at their intersection, it's bounded. So the subgroup sits in here, and the index is independent of the prime, and it only depends on the dimension. And then there's the other way. So we're saying they're commensurable, but uniformly, independent of L. So that's what I mean by look like. So the same thing. And so when we look at the other way, it's again uniformly bounded D, but now there's one other thing, which is just exactly this cyclotomic stuff we talked about earlier. So in particular, it doesn't depend on the actual A chosen. Okay, so it's an effective version of what Serre was doing. Serre, just all his constants depended on the initial abelian variety A, and here's it sort of stripped away so we can see how things depend on the dimension in the field. Okay. Connective. Also, it doesn't matter because of this finite index, I can always just decrease this to the connected thing, and it still doesn't. Yeah, for me, it means connected reductive. Yeah, I don't think it's well known how you construct the connected component abstractly. Yeah, Serre only constructs sort of the connected piece. So if you looked at the L-adic one and looked at its reduction, he's only constructing sort of from first principles the connected part, not the components. Okay? Great. It's in some cases you can, in some cases you can't. The theorem, it's harder to do it in prime cases level, but you can deduce it later in some cases. Because usually big mod L image means big L-adic image. So you usually get it for free later. It's hard to prove at this point, though, to consider powers of L. Okay? Yeah, so there's sort of two new things in here to make it work. One is these massive Stolz thing, which if you for effective faulting, effective taking, yeah, effective. Yeah, yeah, not the full thing. Yeah, so that's you probably saw this and recognized master Stolz. The other thing, Serre uses a theorem of Jordan, classical one, where if you have a finite subgroup of GL2G complex numbers, there's an abelian subgroup of bounded index, which is normal. And I'm using a version of Pink and Larson where you allow various other fields. So both of those effective ingredients make this theorem effective, and actually you skirt around the hard parts of Serre's proof, which was really ineffective, like Hermite's theorem and stuff. Okay, and I'm out of time, so let me just say two things. One, what actually should be true is these HLs should all be the same. They should all be the reduction, for L big enough, the reduction of a single group, Mumford-Tate group or Motivic-Galois group or whatever, connected component of, whatever you like. How you end up proving the theorem is you try to figure out what this group HL is, and it turns out once you know it has the right rank, you immediately deduce that it's GSP2G. So it's just a question of computing the rank of these groups for L big enough. And once you show they have big rank, you find that H is GSP, so this image looks like GSP. And there's really no interesting sort of bounded index subgroups in the symplectic group, so then you get the full GSP. Okay, so that's the ingredient. So yeah, so to summarize, if you have a family of abelian varieties, you sort of know what the Galois action is most of the time. And to actually study it, it's effective Hilbert irreducibility with this kind of information of Serre saying what's happening for each prime L. And the answer is it should look like a group, a reductive group. Okay, so my voice held up just long enough, so thank you.